Hi everyone, welcome to our class. I want to continue with the homomorphisms which we began yesterday. And today we want to look at types of homomorphisms. Of course, we look at only one or two. And then we may look at two others maybe on Thursday, and then we begin looking at rings. Now, so the first type of homomorphism that I will be looking at is the kernel and image. These are two two different things. Kernel and image are two different things. So we'll be looking at the kernel of a homomorphism. We need to know what it is and how to determine it, and then look at the image of homomorphism, and again see how to obtain it. So what is a kernel of homomorphism? Of course, we defined homomorphism yesterday, and we said that it's just a mapping from one group that real condition. And the condition that we talked about, we said that this mapping would map this and this dot would mean either addition or multiplication. So this will be mapped to phi of A and then phi of B, where again the star here would mean addition or multiplication. So if sorry for that. I think it's an issue of network. I was just trying to recap what we did yesterday so that we remember what we did as we proceed going forward. Now, so I was just defining what a homomorphism is, which we defined yesterday, and we said a homomorphism would just be, for instance, we would say that phi, the function phi is a homomorphism. That is, supposing I have a b, then this would give me a phi of a, then phi of b. Of course, what we say is if this star would mean either addition or multiplication, and again this would mean either addition or multiplication. So that if it's multiplication here and then multiplication here, if it's addition here, again it will be addition here. So a homomorphism would preserve the operation of the groups, the operation. Now, so what is the kernel of a homomorphism? The kernel of a homomorphism. So the kernel of a homomorphism, and you see this now, this is a homomorphism. So the kernel of this homomorphism is a set of elements in the first set. This first set, we call it the domain. It is the first set here, you call it the domain of the function, the domain of the function, and this second set, we call it the codomain. Codomain of the function. So we have those, we have the n and the domain. We have else is on the codomain. So just one.
It seems Mwalimu is having network issues.
It seems my internet has challenges. Now, so I had explained what the domain is and what the codomain is. So the set of all elements in the domain that maps to zero, that is, if you're talking about an additive groups, then the identity is zero. But let me use the word identity because if the group is additive, then the identity will be one. So those elements which will be mapping to the identity is that those are what we call the kernel. For instance, suppose this is our H 0, 3, 4. And let me say that this H is an additive group so that the identity is 0. And suppose we have a group G. Let me draw it properly. Yeah, I just want to illustrate what we mean by the kernel so that we proceed. Sub X, Y, W, N. And supposing that we have this function phi, which is mapping elements of G to those of H. And suppose it maps X to that, and maps Y to this, and maps W to this, and maps N to that. So the kernel, therefore, will be the set of elements which have been mapped to 0. The identity element in H. The identity in H is 0. So the kernel is therefore W and N. This is what we call the kernel. The set of elements in G which are mapped to the identity in H, which are mapped to the identity element in H. So you can see that W has been mapped to the identity element, and N has also been mapped to the identity element. This is what we call the kernel. And what about the image? What about the image? So the kernel, we've said that elements in G which have been mapped to the identity element, those are what we call the kernel. What about the image? Now the image, we consider this codomain. Consider this codomain. Inside this codomain, you can see that we have elements which have been mapped to. Elements which have been mapped to. And you can see that there are other elements which have not been mapped to. For instance, 3 and 4, those elements which have been mapped to, the set of elements which have been mapped to. For instance, in this case, our image is the set comprising of 1, 2, and 0. The set of elements in the codomain which have been mapped to is what we call the image of a homomorphism. So you need to know what the kernel of homomorphism is. The kernel, we are considering this domain. We're considering the domain. And then we are checking which elements have been mapped to the identity. Which elements have been mapped to the identity. The set of those elements becomes the kernel. What about the image? We consider the core domain, and then we check the elements which has the image. So that is the definition of the kernel and image. But now we can also define it mathematically. I've just explained what that definition is so that when we define it mathematically again, we can understand the definition. So mathematically, what we say is that the kernel of the homomorphism phi is the set. So once you open these brackets, you mean the set. You mean the set. Those are elements of the set. So is the set comprising of elements G which are in the domain such that that G is mapped to the identity in H. That G, you see G is in G. This G is in G. And that G should be mapped to the identity in H. That is what we call the kernel of a homomorphism. So there is a subgroup. The kernel will always be a subgroup of the group G, of course. That's what I wrote below there. So in cryptography, how important I've said in cryptography, the term kernel, first of all, what does it refer to? It will refer to a variety of concepts depending on the context, particularly in cryptographic algorithms, lattices, and ring algebra. It will refer to a variety of concepts, but when you look at those concepts, it's like they mean the same thing. They mean the same thing, but now defined as slightly differently so that to be used in that context. For example, when you are considering public key cryptography, if you're considering public key cryptographic systems, the kernel will be defined as the set of elements that map to zero during operations, system operations. But when you're considering public key cryptographic systems, so we are referring to things like RSA and so on. And then the term kernel would be defined as the set of elements that map to zero during operations. Operations that we are talking about encryption and decryption. What about in the homomorphic encryption? Homomorphic encryption, what would the term kernel mean? It would mean all inputs that generate encrypted results that decrypts to zero. So if you have inputs that will give us an encrypted result, but that encrypted result, when you decrypt it, get zero, and then those inputs are what we call the kernel. The set of those inputs is what we call the kernel. So you would encrypt them. You will encrypt those elements. So you have those elements, you encrypt them. After encrypting them, when you decrypt, they give you zero. Then we call them the kernel in homomorphic encryption. So you can see it's also used in homomorphic encryption. It's used in very many places in in cryptography. In elliptic curve cryptography, we can also use it. The kernel is also employed there. But what does it mean when you are doing elliptic curve cryptography? What does the term kernel mean? It will mean the set of points on the curve, that elliptic curve, on the elliptic curve, that will be mapped to the identity element. So we have the elliptic curve. You have the elliptic curve, but the elliptic curve has points. And now you want to map these points. The points which will be mapping the identity element. Now the identity element in the elliptic curve is infinity. Is infinite. When we're looking at the elliptic curve, you'll know what the identity is. You see, an elliptic curve is just a group. It's considered as a group. And this group, the identity element is not 0. The identity element is not 1. The identity element will be infinity. This group of elliptic curve. So those points on the elliptic curve, they form a group. They form a group. So what you're saying is, what is the kernel therefore in elliptic curve cryptography? It will be the set of points on the curve that will then be mapped to the identity element. I've told what the identity element is in elliptic curve cryptography. So in elliptic curve cryptography, the identity element will not be 0, will not be 1, it will be the infinity. When we begin looking at elliptic curve, you will see how that comes in. Now let's look at example. Before examples, I already defined the image. I already defined the image of a homomorphism. And I'd said is the set of all elements in H, the codomain, that are mapped to. The set of all elements that are mapped to is what we call the image. So I want to draw a diagram here just, and I'll remember when I'm giving you the notes so that I give you this diagram to assist you remember. So my group G, then I have my group H. H. And then I have the homomorphism. Homomorphism is just a mapping. It's mapping from elements of the one group to elements of the other group. Elements of one group to elements of another group. But it must fulfill some conditions as we saw. So let me suppose that this has elements A, B, C, D, E. And let me also suppose that this has elements 1, 2, 3, 0, 1, 4, 7. Just 10 elements of the group. I want to assume that this is an additive group. So let this element be mapped to that. Let this one be mapped to that. Let this one be mapped to this. And let this one be mapped to that. And let this one be mapped to this. Now, so the question is, what is the kernel? What is the kernel? So the kernel of phi, with the set of elements that map to the identity. I can see that one of the elements is C and the other element is E. So these have mapped to the identity. What about the image? What about the image of this homomorphism? The image of the homomorphism, I'm considering elements of H that have been mapped to. So the elements of H that have been mapped to, 1 has been mapped to, 2 has been mapped to, 0 has been mapped to, and then 7 has been mapped to. So this is what we call the image of this homomorphism. So the rest, we don't have a name for the other elements actually. We don't have a name for 3 and 4. The name that we have is for the image and the kernel. So the image, those which have been mapped to, is just like in English. In English, when we talk about the image of something, there must be an object and there's a mirror. So this object, you can see its image behind the mirror. So for instance, I can see the image of A behind the mirror. The image of A is 1. And the image of B behind the mirror I can see is 2. The image of C I can see is 0. The image of D I can see is 7. So behind the mirror, and I can see the image of E is 0. So that's what we call the image. So all those elements in a set, we call them the image. I hope that one makes it even easier now for us to understand. Is. So we do not have, this 3 is not an image to anything. It's not an image, and this 4 is not an image to anything. Good. So how do we find the kernel, therefore? Find the kernel and the image of the homomorphism. This homomorphism defined by, okay, so what we need to understand the definition of the homomorphism. Just as we were doing yesterday, what is saying, this is the image. Now, this is the image of the element here. So the element here is mapped to the element here. It's this function that is mapping this element. And where is it mapping it? It's mapping it to itself. It's mapping it to itself. Now, so we are mapping from, this is the domain, as we've already explained. This is the domain of the domain of this homomorphism, and this is the codomain. The codomain. It's saying that this homomorphism maps an n here to an n here. That's what I'm saying here. It maps an n to an n. In other words, it will map 2 to 2, to map 3 to 3, to map 4 to 4, map 5 to 5. That is the definition here. That's what the definition is saying. Once you understand the definition, it becomes very easy. Now let's see, what are the elements of Z? What are the elements of Z? Because we've been asked to find the kernel. So the kernel, we want to see which elements would be mapped to 0. Which elements would be mapped to 0? So let's see. Z has elements dot means they continue to the left. I have element 18. I have element -17, -16, -15, -14. Let me say all the way up to, okay, let me just continue. This is -14, -13, -12, -11, -10, and so on. What about Z6? Z6 has elements 0, 1, 2, 3, and 4. No. Then 5. Now, so I just want us to discuss. Where do you think, because we've already said that n is mapped to n. In other words, 2 is mapped to 2. 3 is mapped to 3. 4 is mapped to 4. Where do you think -18 is mapped to? Where do you think -18 is mapped to? I just want to discuss so that we'll see. Where do you think -18 is mapped to? Okay. You see this numbers continue. So when we reach 0, we know that 0 will be mapped to 0. We know that 1 will be mapped to 1. We know that 2 will be mapped to 2. We know that 3 will be mapped to 3. We know that 4 will be mapped to 4. We know that 5 will be mapped to 5. So let me give you a small example. Where will 6 be mapped to?
It will be mapped to 0.
So the important thing is mapped to 0. Yes, 6 will be mapped to 0. Because we are using this n mod 6. It is n mod 6. So 6 will be mapped to 0. Because 6 mod 6 is 0. So 6 will map to 0. What about 7? 7, 5, 7 will map to 7 mod 6. What is that? 7 mod 6 becomes what? If 6 were to go into 7, the remainder is 1. Is that okay? The remainder is 1. So 7 will map to 1. What about 8? Where would 8 be mapped to? 8 will be mapped to 8 mod 6, which is what? 2. So 8 will be mapped to 2. What about 9? 9 will be mapped to 3. Is that okay? What about negative 18 mod 6? So in other words, if 6 were to go into negative 18, what would be the remainder? And you can see the remainder is 0. So negative 18 will be mapped to 0. What about negative 17? Where will that be mapped to? To be mapped to negative 17 mod 6. So the way we're doing this, we're adding 6 to negative 17 several times until you get a positive number. Until you get a positive number. And of course, that is how we also be writing the code for this. So when you add 6 to negative 17 once, you get negative 11. When you add another 6, you get negative 5. When you add another 6, you get 1. So this is not 1. You can do it that way, or if you don't want, you can do it the same way we did earlier. We said 6 will go into negative 17. How many times? You go there, negative 3 times. Negative 3 times. Then negative 3 times 6 give us negative 18. When you subtract negative 18 from negative 17, you have 1 as the answer. So 6 will go into negative 17, negative 3 times. That gives you. So you can use this method, or you can use the one of addition. It's only just adding this one there several times until you get a positive number. When you do that. Now, so let's now see, because we wanted to find the kernel. And there's something I'm saying. Here. See, like this one gave us 0. Negative 18 was mapped to 0. But I'm looking at how do we get, I'm looking at how to come up with a general thing, a formula for getting the kernel for this type of question. Negative 18 was a number divisible by 6. Then I also found out that 12 also, 6 itself will be mapped to 0. So 6 also divisible by 6. 12 is divisible by 6. 18 is divisible by 6. 32, 36 is divisible by 6, even 30. So all those numbers which are divisible by 6 will be mapped to 0. Mapped to 0. Even 30, for instance, 5 of 30 would be 30 mod 6, which is 5, which is 0. So 6 would go there 5 times, and the remainder would be 0. phi of 42 will be 42 mod 6. 6 were together 7 times, the element will be 0. So all numbers which are divisible by 6 will be mapped to the identity element for this question. We map the identity element, and therefore they comprise the kernel of this homomorphism. So that's why I said in my first sentence, I said that the domain, which is Z, of course, I was just defining what it is. I said it's a set of integers and addition. And the code domain, the one we are mapping to, which is Z6, is the set of integers mod 6. Of course, those are just 0, 1, 2, up to 5. So the kernel, then I said, would consist of integers in Z that map to the identity in Z6. So the ones which will map to the identity are those which are multiples of 6. That's why I said, for us to find the kernel, we need to find numbers which on division by 6 would give you a remainder of 0. Numbers which on division by 6, that's what the definition is telling us. The definition is here. That's what the definition is telling us. Numbers which on division by 6 would give you a remainder of 0. So numbers which are divisible by 6. And there are so many. There are so many. And therefore, our kernel is this. This is our kernel. Numbers which are divisible by 6. Even 24. 24 is divisible by 6. Even 30, no, negative. Even negative 36. And so on. And this side, we can also increase the same thing. 24, 30, 36, and so on would comprise the kernel. So the most important thing is knowing the definition. Knowing the definition of the homomorphism. Now, what about the kernel? We discovered that all the elements were mapped to. For instance, our Z has very many elements, very many elements. You have 1, 2, 3, 4, 5, and so on, and so on. We have even negative 18, and so on. But then the Z6 has only 0, 1, 2, 3, 4, 5. So you can see all these elements will be mapped to. All those elements will be mapped to. All of them will be mapped to. And so the kernel is the entire core domain. The entire core domain, no, not the kernel, the image. The image is the entire core domain. All those elements will be mapped to. So in this case, none of the elements will remain unmapped. So the kernel, the image is the entire core domain. That is the image. Can have so many examples. Can have so many examples to illustrate that. But first of all, I want us to look at the Rust code that will give us the kernel and the image at the same time if you are given a question of this type, where Z is mapping elements to Z6. You can modify this and use any number here. You can modify and use any number instead of 6, it will still give you the results. So the following Rust code calculates the kernel and the image of the homomorphism defined as this, where this is the definition of the homomorphism. And this statement is just telling us the definition of the kernel, which you already have, that the kernel would consist of all elements in the domain that map to the identity. Of course, if you know that, then you can write the code. And what about the image? The image are all the elements of the code domain that are mapped to. Now, so this is our code. And last time I had explained the importance of hash set. Hash set is just to ensure that we do not repeat. It helps us to avoid repetition. So that after you've collected your elements, if any element comes in that is similar to the one which has already been collected, then it will not be collected, because we'll be collecting elements. So if there is one that comes and is similar to the one we already collected, then it will not be collected. So in so doing, you avoid repeating. So that is why we use hash set, just to ensure that there's no repetition. Now, yesterday I told about this Unicode. This will mean phi maps Z to Z6, where phi of n is mapped to n mod 6. Now, so this part is just define the homomorphism for us. It's just define the homomorphism and how it will be working. So what does it say here? It says, let the result be n, be the remainder of n on division by 6. Let the result be the remainder of n on division by 6. That's what it means. So for instance, if we have 7, then the result would be 7 divided by 6. This result is 1. The remainder of 7 on division by 6. If our n is 8, then when you write 8, that 6, we mean 2. Because we mean, what is the remainder of 8 on division by 6? So that is what this is saying. So let the result be n, the remainder of n on division by 6. Then this here, it says if the result is less than 0, if the result is less than 0, for instance, if n is negative 7, what it says is that then you will obtain a new result by adding 6 to it. And that's what we did. We add 6 to it several times until we get a positive number. So for instance, if our result is negative, if our result is negative 7, this is not what we write. We would add this 6 to that. When you add to that, you get negative 1. This is not a positive number. It's still less than 0. It's still less than 0. So since it's still less than 0, we would still add 6 to it and get 5. So that's what it says. That if the result is less than 0, then we add 6 to it. And then is the result. obtain is therefore answer. So that is, at this point, it's just defining homomorphism and what will be happening in the process. So I think this first bit we've understood what it means. We've understood what it means. Of course, we know what I32 is, that we'll be dealing with the positive and negative numbers at this point, and there are 32 bits. If you want, you can increase or even bigger, you can increase. So that's what we're saying. Our n here can be either positive or negative. So that is, we can have n which is negative 18. If n is negative 18, then what is the result? Because this negative 18 is less than 0. So the result therefore becomes plus 6 less than 0. So add another 6, get negative 6, which is still less than 0. So you add another 6 and get 0. So 0 now becomes the result. Now, so this is just a definition of a homomorphism, how it will be working, But now we have to, what we wanted is to obtain the kernel and also obtain the image. That's what we wanted. And let's now proceed to obtaining the kernel. And it says, find the kernel. And it notes that the kernel will be elements of the domain. To be elements of the domain. And these elements of the domain are I32. In other words, they'll be positive or negative. But now, when you enter those elements, what you get will be a vector. What you get will be a vector, and that vector is still I32. So you enter that element, and of course, it gives you a vector. That vector is still I132. Now, so how will this code therefore be obtaining the kernel? So let the kernel be mutable. Let the kernel be mutable. So in other words, it will be changing from time to time. Because we'll be collecting elements. So we go through all the elements. Supposing the domain given to us has 0, 1, 2, 3, 4, and so on up to 13. Supposing this is the domain. So first of all, we have no elements inside there. We have no elements. We begin with it when it's empty. Then we go through all these elements. Go through the first one, see whether it fulfills the condition that it will be mapped to 0. If that is the case, then we say that our kernel has one element. Then we consider this other element. We want to see whether it will be mapped to 0. If it's not, we don't consider it. So we come to the next element. So if we discover the next element is mapped to 0, then our kernel increases, now has 2 elements. And then we consider the next element, we consider the next element. If we discover that 12 is mapped to 0, and if we discover that these are the only elements, then we close the bracket. Now we have our full kernel. So you can see how mutable it was. Began with no element, then gained the first element, then it changed again when it gained the second element, then it changed when it gained the third element. That's what I mean by mutable. Mutable. That's what I mean by this mutable. So it means that it will be changing from time to time. It's not fixed. It's not fixed, so it will be changing. Now, so I just want to explain what this means. We will say that it will be changing. And then, of course, it will be in the form of vector. form of a vector. Now, this dot iter, it means iteration. So be iterating from one. So that is what we are saying is you consider the first element, consider the second element. That's what you mean by iterating. Moving from this, consider this, and going all around through all those elements. Going through all those elements. That's what this first bit is doing. So it's going through all the elements of the domain. Going through all the elements of the domain, looking for the ones that will be mapped to 0. So this is now what is looking for the ones mapped to 0. So this iterating means we begin with the first element, check whether. Now, when we go to the first element, this part now checks this part. Filter says filter. Filter n, where n which is mapped to 0. Filter n that is mapped to 0. This homomorphism. Look at this. This homomorphism. So this homomorphism has been defined above. Has been defined here. It is here. So, what this one was doing, it was finding the homomorphism. It was finding, supposing the elements -18, -17, -16, negative. So what this one was doing, it was just dividing this element by 6 and noting the remainder. For instance, this one divided by 6, the remainder of 0. This one divided by 6, the remainder of the 1. This one divided by 6, the remainder of the 2. And so on. And again, when you reach to 12, the remainder will be 0. When you reach to 6 here, divided by 6, the remainder will be 0. So let's come back to filter here. Filter n, where the homomorphism of n is 0. Filter n such that the homomorphism of n is 0. So in other words, just come back here and check the ones which gave us 0. That's what I mean by filtering. Filter those ones. That's what it means, filter. So this one, the first bit had done some work for us. It done some work. It had divided by 6, 6, 6, 6, and noting the remainder. So when you come to filter now, it goes back and checks those which gave us 0. That's what I mean by filter. Then there is collect. Then there is sort. No, sort is not important. Sort, I just used it so that it sorts the elements and arrange them. Sorting, I just want them to be arranged in some order so that you don't confuse. So that one comes up before 2, so that 2 comes before 3, 3 comes before 5. This is what I mean by sort. I just wanted to sort the elements. Then collect, of course, we just collect the elements. So from then there's clone. Does not have a lot of just as sort does not have a. Now the same thing for the image. You can see the image is the same thing. So I don't need even to explain them again, because these are the same things that are above. But now what is the image? Elements which have been mapped to. Elements which have been mapped to. So the difference only comes here. But look at this map n, homomorphism of n. The other one was filter. Taking the homomorphism where This one, we want to see where n is mapped to, where n is mapped to. So you go back to the homomorphism there and see where has n been mapped to, and so on to which have been mapped to. You collect those which have been mapped to. There's this hash set to ensure that you're not collecting an element twice. If it's already collected, you don't collect it again. That's why you have hash set. Of course, we know what iteration we'll be doing. I just want them to be arranged in a way that you can easily see that this element has been collected, this one has been collected. Let me just share the code. We see the code first before I explain the notes. Okay, that is the code. Begins with that hash set, and we say what that one is. You can see it. Is that okay? You can see the code. Huh? Or my internet is not stable. Okay, let us run. I thought I pressed enter. I think my computer is a bit slow. Supposed to have run this one very fast. Okay, it took some time. I think it's not that the code is not that it's long. I think computer is slow. But you can see it has given us the kernel as the elements which are divisible by 6. So it begins with the dot dot, meaning that they continue. This element is divisible by 6. This element is divisible by 6. So this is what I sort will be doing. Sort is arranging those elements in some order. If you remove sort, then these elements will just come in any way, will just be mixed. And even also the same thing for the image. If you remove sort, then these elements will just mix up. Yes. And that is why if you remove sort, then they would just come in any order. Now, if you remove hash set, then you may find some elements being repeated. So hash set is just to ensure that none of the elements is repeated. Oh, let me just again share. Now, what is the main? What is the main? That is why you define the main is where you define your range. This is where you define the range. So the range here is from -30 to +30. But if you want, you can increase it. Let's try and increase to 100. Let's see. -100 to +100. So this one, just increasing it's now to define the range. So we want to see the kernel in the range given to us now. You can see now it has begun with negative 96, and the kernel will be elements which are divisible by 6. You can see that is still considered, and they have been arranged in a given order, and the image remains the same thing, because our codomain had only 6 elements. Our codomain had those 6 elements. Now that code, you can customize it. You can customize it to give you the results you want. And you can also change the groups. You can change the groups so that you have the kernel for the groups you want. I've already explained the first bit. What it means, I've said that this would calculate n mod 6. So it's going through all the elements of the domain and getting their remainders on division by 6. It's going through all those elements and getting their remainders on division by 6. If an element is less than 0, it will get that remainder on division by 6 by adding 6 to it several times until you get a number that is positive. So the first time you get the number that is positive, that is okay. A number that is positive and less than 6. So you add 6 to that negative number until you get a number that is positive and is less than 6. So that is what this code, this part will be doing. I said that it will begin. So going through all the elements of the codomain, and then filter. It filters the elements where the homomorphism equals to 0. So of course, that means it will go back to number 1. Number 1, check where the homomorphism, where the elements were giving us 0, then filter. Then it collects these elements. After filtering them, it collects them. Those which homomorphism equals to 0, collects them. Them out. After sorting, what you have is a kernel. Of course, does not have a lot, but it does not mean that it's not useful. Now, so from this part going down, I now wanted to explain what each part does. I wanted to explain what inter does, creates an iterator over the domain, allows the function to process each element, then filter what it does, then this part, what it does. So I was going through every function, every sign. There is clone. So what I was saying is, what does cloned do? Cloned creates a new collection with the values that are I32. So what it means, after iteration, we have elements. So cloned will take those elements and create new elements for those elements. So creates other elements that are. Now this is supposed to be this. It's supposed to be this. Is important. Let me just write it properly there. This is important because the vector I32 that will be returned must hold actual integers, not references. So that is what the explanation here is the importance of cloning. The importance of cloning is what I'm explaining there. And then we have collect. And then we have, after that, we have the kernel coming out. Once the kernel vector is populated, once we have done enough kernel, it comes out after being sorting and so on. What about the image? Is the same thing. Now the image, let the image be mutable. Of course, it will come out as a vector, I32. That is what we have here. That's what we have here. Find the image. We take the elements of the domain, which are I132, then they'll give us a vector. What comes out will be a vector. That is I132. So I began by first of all explaining what the image is, and I've said the image of the homomorphism is a set of all elements that are mapped to. Now, so I'd give an example. Supposing you have Z, and we're mapping to Z6. So we are looking at what elements of Z6 will be mapped. And you can see in this case, each of these elements will be mapped to each of these. Because you see this set that are here, all the elements that are here are also here. So definitely they'll be mapped to the ones that are here. And then we have also those ones, the others, which are not exactly the same, but are multiples. Those which are here and are multiples of 6 will also be mapped to 0. No, will also be mapped, not necessarily to 0. Not necessarily to 0. If I say 0, I'll be still talking about the kernel. But every element that is here, would map to an element here. Would map to one element here. For instance, 17, which is in Z, would be mapped to 17 divided by 6, the remainder of the 5. So it will map to 5, and 5 is here. 16, map to 4. 15, map to 3. So each of the elements in Z would be mapped to a different element, mapped to a different element in Z6. So all the elements in Z6 would map to. So they'll all form the image. Of course, at this point, I will again explain the use of the hash set. Oh, this one here, hash set. Saying the results are collected into a hash set to ensure uniqueness. In other words, to ensure no repetition, no duplicates. To avoid duplicates, to avoid having elements occurring more than twice or more than once. Then again, the image is sorted. So again, we ensure that elements are sorted so that they are arranged properly. Now this sorting, I placed it later when I discovered that when I was doing this, it was giving me elements haphazardly arranged. So you would find it giving you, for instance, the image, give you the image as 2, 5, 1, 0, 4, then 3. So you see, this is a bit confusing. So I thought so that they are arranged in the order 0, then the next smallest number, then the next, and so on. So when you want to do that, then sorting has to come in. So that is why sorting is important. Good. I think that is okay for today. So it's enough for today. So what you need to do is look at how to find the kernel, and then apart from, just take my code and see how to customize it to do for you various things depending on your tastes, what you want to do, and so on. Thank you. The class on Thursday. We'll get communication for that class.